So I'd like to introduce our two speakers today. First is Dana Linnett. She's a senior executive for quantum market engagement with Artificial Brain, and she'll tell you something about the company. Dana is CEO of the Summit Group DC, specializing in defense, aerospace, and emerging technologies. She also serves in multiple advisor roles, including with Donovan Capital Group and the Roosevelt Group. She was previously a U.S. career diplomat, a global VP GM for a series B2C tech startup, a growth leader for a $2 billion PE-owned consultancy, and an international defense OEM executive. Dana brings 27 plus years of leadership experience in consulting, government affairs, business development, international trade and export, and government contracting. She will be joined today by Jitesh Lalwani, who is technical founder and CEO of Artificial Brain. Jitesh is an accomplished software industry professional with 15 years of experience in software development and team management. He has worked with diverse technologies such as mobile development, AI, machine learning, and quantum computing. He has successfully handled a multi-million-dollar Euro project and was responsible for hiring and onboarding 100+ engineers for his previous organization and leading a team of 60+ engineers. In the past, he created a viral Android app called Free Call app, which allowed users to make free calls to their friends in India over a poor network such as 2G. So with that, I'm going to pass it off to Dana. And again, welcome to our friends at Artificial Brain.
Thank you so much, Susan. I also want to introduce Amit Patel, who's one of our engineers and is going to be helping us with the program today with Q&A, and he's very much a core part of our team. Good morning, good afternoon, good evening from wherever you're joining us from. We appreciate you stopping by our webinar today. We very much appreciate D-Wave and Susan for giving us this opportunity to highlight for you and talk to you about the algorithm which helped us win the prize, which we'll get to. Artificial Brain does many things in the space domain and satellite domain, but we're going to focus in on Earth observation, satellite mission optimization, leveraging Artificial Brain's quantum computing algorithm. So who are we? We are a quantum computing software company, and we develop the optimization software, and our specialty really is the space, energy, and aviation field. Okay. And this is our team, Jitesh, who's the founder and CEO, myself, we just heard the intro. Dr. Pandey is our research and development expert, really deep into this technology. Raphael Rudigen is our advisor who has funded space startups. He's very well known in the space sector. Bill Gonzalez, one of our advisors, is also longtime expert on machine learning and quantum technologies, and we can't tell you what he does because he'd have to kill us. Craig Connell is our advisor doing commercial tech and growth and has a lot of CTO experience, which he's helping us to leverage right now. So this is basically our core team plus Amit, which we cannot underestimate. So next slide. So I'm going to turn it over to Jitesh, who's going to talk to you about why quantum for space. Jitesh?
All right. Thanks, Dana. First of all, thank you everyone for taking time out today and joining this webinar. And also, we would like to thank D-Wave for providing us an opportunity to present our work today. So first, let's talk about why quantum for space, right? So as you might have heard that already agencies and private companies are using quantum communications. They are exploring how quantum communication, QKD, or quantum security can be used for satellite to satellite communications or satellite to ground station communications. We as a company are, as Dana mentioned, focusing on developing applications, and as we all know that space exploration and activities are highly complex in nature. There are many use cases which are also known as NP-hard problem, or it takes many years for classical computers to develop them. For example, when we talk about rocket design optimization, or the algorithm that we have worked, which is Earth observation satellite scheduling optimization or fuel optimization and so on. On top of that, many of the activities, they require dynamic decisions, right? So when your rocket is in space, right, or if the space debris is near to a satellite, there are many places where you don't have enough time, where you can go back to classical computers, wait for a couple of hours to get optimal results. And this is why quantum can have a very big impact in the space industry. On top of that, there are a lot of business opportunities for quantum companies such as us. For example, we can help space companies to optimize lot of their operations, and we are talking already billions of dollars, right? We can save billions of dollars for this private space companies and also space agencies such as NASA in the US, or European Space Agency, or EUSPA in Europe, or even ISRO in India. So that's why we as a company, we believe in this area, and that's why we are focusing our lot of energy and efforts in developing space applications. Now let us talk about Earth observation satellites. So these are the satellites which are being launched by private agencies and space agencies, and these satellites are launched and they orbit Earth within 200 to 2000 kilometers above Earth, which is also known as LEO. And there are many applications when we talk about Earth observation satellites. So initially, the first application was spying, right? But nowadays are so many applications where private companies are also investing a lot of money in developing and launching their own satellites. The first application, which is very important for governments around the world, which is fire monitoring, right? So when there's a fire in a forest, government would like to understand how big is the fire, how long is the fire, what are the optimal resources that can be deployed to stop fire immediately. And this can be easily done using Earth observation satellites. The second application is water pollution monitoring. This is where companies working in water management, treatment, and government agencies, they can monitor what is the pollution of water, and accordingly they can do the treatment of water. The third, which is one of the most important applications, which is crop monitoring and farm optimization. Agriculture companies, they would like to understand how their crop is performing, and this is why they take the help of Earth observation companies to do their crop monitoring and farm optimization. Now let us talk about our quantum algorithm, which is basically scheduling optimization of Earth observation satellites. So before talking about the algorithm, let me talk about the problem statement. So as you can see on the left side image, this is a satellite which is orbiting above the Earth, and these small black dots are also called as observation areas or targets, which needs to be captured by this satellite. Now each of this observation area has different priority value or different business value. For example, this small dot, it can fetch, let's say as an example, $100 to Earth observation company, and this dot or observation area might fetch only $20. And this dot, even though it might have less business value, but in terms of priority, this might be the highest priority. For example, if this is a observation area of a burning fire in a forest, right? So even though the business value might be less, but the priority would be higher. So on top of that, your satellite would have limitations such as storage limitation, energy limitation, and many other constraints. For example, if it's a thermal camera which is put on satellite, it will also need some cooling period. And obviously there's weather also involved. So even though if an algorithm is able to satisfy all the constraints, but the weather is poor, the image or the observation that would be captured by the satellite would be very poor. And on top of that, these satellites are always moving. These green boxes that you see, these are basically ground stations, or these are the stations where the satellites, they send their data while they are above these ground stations. So if the satellite is not within the range of these ground stations, then the satellite cannot transmit data back to the earth. And there is also something called as downlink window time. So if the image has to be transmitted properly, the satellite has to be above ground station or within downlink window time. And on top of that, if there are more than one satellites, there can be certain observation areas or targets which might be overlapping. For example, this blue color box is overlapping within satellite S1 and S3, and this box is overlapping between S2 and S3. So now you can understand how complex it is to capture observation, and that's why this is also known as oversubscribed problem, because there are always many observation areas that need to be captured than a particular satellite can handle, and this is also known as NP-hard problem. So what we have done is basically, as you can see on the screen, let's say these are the observation areas which this particular satellite needs to be captured, which this satellite needs to capture. But as I mentioned, each of these observation would have different priority value and different business value. So our algorithm would help to identify which are the optimal observation areas that the satellite should capture, such that the target should satisfy all the constraints. Second, the combination of the business value should be the highest. So as you can imagine, there could be multiple combination or millions of combination in which this target could be selected. But our algorithm would always try to find targets with highest business value.
So just to sum up, we have a lot of satellites proliferating in space, or maybe a company has only a small number of assets in space. So whatever the space assets are, we know that there's a limited time overhead, communication window with the ground station, and maybe you have multiple targets and you need to find the optimums for which targets to hone in on at which time of day, with which weather, with which type of optical camera, whether it's thermal or infrared or other. And so you have these many degrees of difficulty, if you will, these constraints, and it can be very costly for a space company or a satellite company to know exactly what to target when for the highest, not just the highest business case value as we talked about, but also maybe the emergency value, the urgency value. And so the quantum algorithm will optimize that in a way that classical computing can absolutely not handle at this degree of difficulty or this degree of complexity. So wanted to sum that up.
Yeah, thanks, Dana. And we will also give a demo today, and we will also present our benchmarking results, where we have benchmarked our quantum algorithm versus classical, and we will demonstrate how classical did not only perform poorly, but we have to stop the algorithm in middle, because once the data size increased a lot.
Right. When you get to certain data size, it just ceases to work. So there we go. We're getting into the algorithm now.
All right. So let's talk about the objectives before talking about objective function. So there are two objectives of this algorithm. The first is to find targets having maximum priority or maximum business value. So here, as you can see on the screen, this is summation of Pi into Xi. So Xi represent your targets and Pi represent priorities of those targets. The second objective, as I mentioned already, that even though if you are able to capture all the images, if the weather is not good, you can't send it back to Earth. And if you are not able to send it back, then it is a wastage of energy, time and efforts, right? So we also have to make sure that whatever targets we are selecting, those are in good weather and we can safely downlink them. And if we combine both this objective, the mathematical, so obviously I'm not going to go into detail, but this is just to explain in layman terms that the mathematical formula looks something like this, which is alpha into the first objective plus beta into the second objective. And these alpha and beta are weighing parameters. So we can easily change the parameters. For example, if you want to give more preference to selecting higher priority target, or if you want to give more preference in selecting targets having good weather, or if you want to make a balance and keep both of them as 0.5, we can also do that.
And I would just say on that, while we chose weather as a constraint, there are satellites that have optical capabilities that can see beyond weather. So maybe if you have a satellite with that's weather dependent, or with an optical capability that's weather dependent, but you want to shift to one that's not, you can program the algorithm to optimize which of the satellites with which capability that you want over station or on station at which particular time. So it's just to summarize, we can handle multiple constraints of very complex constraints. So this is both for government application becomes very interesting for that, but we're using the commercial case at this moment.
Some of the constraints are mentioned here: storage limit, energy limit, downlink limit, and there are multiple constraints which we are which we are calculating at the runtime, and this is our secret sauce, right? So there are a lot of calculation which is happening on the runtime. So just to give you an example, let's say if there are two ground stations, right, and if your satellite can capture image and can downlink it, but that image does not have high business value, right? So you don't want to capture that image, rather you want to capture next image which is after ground station 1, right? So we are also calculating all these scenarios, and at the runtime we are giving constraint, right? And this is our secret sauce, and that's why this is our proprietary algorithm. So in this webinar we are concentrating only on this specific algorithm, but there are many other applications which we can talk about later, and this is what we presented last week during Quantum Meets in Netherlands, where we again collaborated with EUSPA, because we have not only won the competition, we have also become part of their network, and we talk about how quantum can be useful for space debris removal or other use cases.
So just for the audience, EUSPA or EUASPA, it's the European Union Agency for the Space Program, and that's the competition that we won. But okay, so do you want to do the live demo?
Yeah, let's do
okay
live demo, because it will be more exciting to see.
Yeah, so for the engineers among us, it'll be more interesting and fun for you to watch this part.
All right. So this demo I'm going to give in a Jupyter notebook. Let me first explain the data. So users or agencies, space agencies, they can give the below data to our algorithm, which is the list of target identifications. These are the observations identification which the satellite needs to capture, and each of the observation or targets, they have different priority values. So these priorities are calculated based on either business value or how much emergency is there. If there's as I mentioned, if it's a burning fire, that image would have high priority versus other images. Then what is the size of target? Because as I mentioned, your satellite has a limited storage. It is not like a cloud where you can keep on storing images. So there is a limitation on the satellite storage. So our algorithm will also take the size of observation and energy, how much energy it would take to capture a particular observation. And these are the storage limit of satellites. So for this example, we are considering 3 satellites. So our algorithm can work for one satellite or n number of satellites. There is no limitation to that. So for this demo, we are considering 3 satellites, and these are the storage limit of each of the satellite, followed by energy limit of satellites. And I will explain this input shortly, but these are the main input that is given to our algorithm. And what we have done, we have made our software available as an API. So right now the software is installed on my local system, but it can be also published over a cloud like AWS or Microsoft Azure. And we want to, the reason why we have done this is we want space agencies and companies to leverage the power of quantum computing without the need to install anything or learn quantum. And the second advantage of exposing or making software available as an API is that it can be integrated in existing workflow. So they don't have to again install anything, and they can use quantum without learning quantum, right? So I already ran it on a D-Wave machine. I already got a response. So let me go to D-Wave machine. So this is Leap. D-Wave is providing quantum computers over the cloud. I just ran on an actual quantum computer, and
Thank you, D-Wave.
yeah, thanks D-Wave for that. And it only took 0.032 seconds to provide a solution, right? And these are the solution that it provided. And topmost, which is how quantum annealing works, is that whichever is the lowest energy, that is your optimal solution. So it provided us optimal solution within 0.032 seconds.
So immediately, basically.
Yeah, almost.
Almost
in real time.
instantaneously.
Yeah. And this is the output which is written by our algorithm. So these are the observation or target IDs among several targets which our algorithm. Okay, sorry, I need to go back here. Okay,
There you go.
Okay,
Back
so
up,
this
yeah.
is the output which is written by our algorithm or by our quantum powered API. So these are the targets which is written by our algorithm, and these targets are written based on two criteria. So first criteria is that the combination of these targets should generate highest business value. For example, this T15 would have, let's say, $200 business value. This T14 would have $100 business value. T11, which is not in this list, might have just $20, right? So our quantum algorithm would try to select combination of targets such that if you add the individual business value, the overall business value would be highest. The second criteria, that these selected targets or observation areas should satisfy all the constraints, right? Because if it does not satisfy one of the constraints, for example, if the algorithm will not satisfy storage constraint, then even though it is fastest or more accurate, the result would be not accurate. And not only that, our algorithm will also inform agencies or our customers which satellite should capture which target, right? As I mentioned earlier that there could be overlapping targets. So our algorithm will also take care of overlapping observation areas or targets, and it will tell you which satellite should capture which targets in what order. So this is regarding demo. Now let me present our benchmarking results. So as I mentioned earlier, we have benchmarked our quantum algorithm versus classical algorithm, and in this case we have benchmarked our quantum algorithm versus simulated annealing, which is just like quantum annealing but it runs on classical computers. And second is the best classifier available in the market today, which is Gurobi optimizer.
Gurobi optimizer, yeah.
So as I mentioned that the goal of the algorithm is to select targets having highest business value. So we calculated what is the mean of total priority. So we generated 82 rows or 82 data set, and each of the row had 1000 targets. So we started with 10 number of targets, then 600, and then finally we choose 1000 targets. So we ran it again 82 rows, and each row was having 1000 targets. And as you can see, the mean of total priority of our quantum is 50,000. Whereas for simulated annealing, it is just 17,000, and Gurobi it is 35,000. So this is a clear indication that the quantum annealing algorithm was able to return targets that can generate maximum revenue for Earth observation companies. The second benchmarking which we did was on the basis of execution time or speed. So quantum was able to execute in 23 seconds. And when I say 23 seconds, this is for all the rows, and it also includes latency time. Meaning when we submit a problem statement to D-Wave, it also goes to D-Wave quantum computers over the cloud. Then it gets executed on D-Wave quantum computers, and then it gets back to us. So including latency time, it was 23 seconds, and simulated annealing performed really well, which is it was able to return result in just 2 seconds. Whereas Garobi optimizer was able to return results in 39 seconds. So this is mean of execution time. So as in this also we can see that quantum was able to perform well in terms of execution time when compared to Garobi, but it did not perform well in terms of execution time when compared to simulated annealing. So these are the two benchmarking which we initially have done, but we were not satisfied with these two benchmarking. So we said, let us go in depth. Let us try to figure out which of the algorithms was able to satisfy all the constraints. So as I mentioned that if some algorithm is faster or more accurate, but that algorithm is not able to satisfy either storage constraint, energy constraint, or any other constraint, then basically whatever data or information that algorithm is providing would not be of much use to Earth observation companies. So this is what we got when we compared our quantum algorithm. So our quantum algorithm was able to satisfy all the constraints for all of the data, right? And this I am talking about 82 rows. Each of the row was having 1000 targets. Then
So 82 rows of 1,000 targets.
Each, yeah.
Yeah.
And simulated annealing performed worse, right? It was the worst of all the three algorithms. It did not satisfy all constraints for any of the data. And this is, so we again started with 10 targets, then 100, 600 and 1000. So when the data size was less, when the number of targets was low, it was able to satisfy constraint for all of the data. But when we kept on increasing the number of input size or the number of targets, then as you can see on the screen, it was the worst among all three algorithms. And then Garobi, it was able to satisfy still for 70 rows out of 82 rows, which is approximately 20-25%. It was not able to satisfy. So it was able to satisfy for 75 to 80% of the data, but not for all of the data. And not only that, we also have to stop Garobi in middle for 22 rows out of 82. So this is where Garobi went into infinite loop. And we unfortunately then have to stop Garobi algorithm after a certain time. And this benchmarking results, we have also published a technical paper where we have presented our algorithm, the results and benchmarking results as well. So this result is not just important for us as a company, but for a whole quantum community, right? So this demonstrated that for certain use cases, quantum can still outperform other algorithms, not just in terms of accuracy and execution speed, but also satisfying all the constraints, which is very important for certain use cases.
And I just want to add something to Jitesh's point, and this is really important. So we only looked at 3 satellites and a finite number of targets.
Yeah.
And in the real world, it would be even more complex than this. So if you think about this as a really simple simulation with a simple data set that's fairly homogeneous in some ways, like if Garobi went into infinite loop on such a few number of constraints in this very tight sort of low level simulation, you can imagine there's no way that it can even stack up in terms of more complex operations and more complex mission operations and the capabilities needed there. So this is why quantum can be used now for these types of problems that AI cannot satisfy.
Okay, so maybe
Yeah.
I go to this step.
Yep.
So then I hand over again
Sure,
to Dana
yeah.
to talk about business opportunities. Yeah.
Yeah, sorry, we're doing our thing.
Yeah.
So why is this important? So if you just look at the commercial space market, we're looking at a growth up to $1 trillion in this space market by 2032. Now that's not even 10 years away now. So we're looking at a huge business growth, huge business opportunity with Earth observation market, which is what we've been focused on in this one very tight use case. So the Earth observation market's going to grow to 11.3 billion by 2031. Again, very short number of years away. It seems like it's far away, but it's not. So when you have this huge market growth for both space and EOS, quantum can definitely help speed this entire market transformation. Maximize the investment and return on investment, but also create highly necessary resource efficiencies, because for this scale of transformation, we're going to need all of the technology opportunity that we can to maximize the resources going into this market transformation on every level. And then next one. And then the quantum algorithms. So we're not trying to oversell the promise of quantum right now and what hardware and software working together can do. But we know now, just from the work we've been able to publish and the research we've been able to publish, that these algorithms can be leveraged right now to create higher return on investments and reduce costs. So don't wait on the sidelines. The future is right here and right now in many respects. And also we get the question a lot, what about AI and where does this stack up with AI? And, I think one of our advisors, Bill, who's a longtime machine learning expert and AI expert, he will tell you about quantum. It's not an either or choice. You can layer in quantum to maximize also your AI results. You could do AI and pre and post processing, which Jitesh runs that all the time in his work. So, layering in with the existing AI means that, you're taking the benefits of all of the investments in the space market and you're taking it to a whole different degree. And we think that society doesn't have the money and the progress to burn. Like, we don't have the time to burn. We don't have the capital and the capital investment to burn, the operational expense, the capital expense to burn. We don't want to leave that money on the table right now by just standing around the edges and going, where's quantum and what's happening with quantum? This is the opportunity where quantum technology leadership is needed. So we're not waiting. We don't want you to wait. The opportunity really is right now. And so I think at this point, Jitesh and Amit primarily will take the questions. On the technical side, I saw there were a lot of technical Q&As about methodology and what we were doing there. So we just want to thank you and thank D-Wave for making your hardware available for us to be able to perform our work. Mm-hmm. It's really critical, and we're very grateful for that partnership. And I will turn it over to Jitesh and to Susan and Amit. Questions.
Thank you so much, thank you both for this. We do have a lot of questions. Some have been answered, but we have lots that we will ask you. A lot of people asked about the paper, so I understand if you go to the LinkedIn site for Artificial Brain, there will be a link to the paper that will talk about their algorithm and the work that they did.
So I can paste it now in the chat here.
Yeah, Jitesh will paste it in the chat real quick.
Great, paste it into the chat. All right. So here are some of the questions. How to choose alpha and beta? Is there any way to make them as variables of your problem?
Yeah, Amit, you would like
Amit, do you want to take that one?
So alpha and beta. So alpha was denoted for the priority value of those targets, and beta is for the weather. So it's basically depends on the subject matter expert, like how good you wanted to go in which direction. If you want to get better priority value in terms of targets, or you want a better, clearer picture. So this decision has to be given to the satellite company or the guys who are using the algorithm. So this, we don't want to put them as a variable in our problem. So I hope that answers the question.
Okay. Have you used any heuristics?
So regarding heuristics, So our classical algorithm, which we have tested again, was simulated annealing and Gorobi optimizer, which kind of one of the best optimizer in classical world. And we have seen few heuristic example which looks like it will exponentially increase the complexity when it is to be solved. So we thought better test against the best, not the second best or something. So which we have done with Gorobi.
Okay, Jitesh, you need to post the link. There's a drop down that says to everyone
Yeah, make it.
in the chat. Okay, did you try this on other quantum machines?
So currently we haven't tried, but initial versions we have tried with our gate-based computer, like with Qiskit and Google and something. But problem with that is that you cannot go beyond, because the qubits are limited, and we cannot go more targets, like more than like 10, 20, 50 or something. But with annealing, we can go quite more.
And Jitesh,
So,
add to
but
that. Oh,
we are in talks with other companies which are like which are creating similar annealing or digital annealers. So we are open to try on those things.
Okay, this question we actually had several times. How can you actually prove that it's optimal? I mean that with quantum annealing, you found the optimal in mathematical meaning value.
So so the basically if you see the priority values which we are showing in terms of Garobi, in terms of simulated annealing, and in terms of quantum. So if you see, there is a vast difference in the result, right? And over there, with those differences, we are saying, hey, this is the better. We are not saying it is the best, but the current competition what we have, there the solution are the best. And we can say it is a optimal because it is satisfying all the constraints, whether the other case in Garobi and the simulated annealing, they were not doing so.
Okay, what is the
It's
maximum number of targets, satellites, and constraints you have tested on an actual D-Wave quantum annealer? Plus, we had a number of questions about whether it was using one of the hybrid solvers or going direct to the QPU. So if you'd answer both of those.
Yeah. So we have tested more than 1,000. So we have tested for 3 satellites. So 2,000 in one, another 2,000 in one, another 2,000 in third one. So you can say 6,000 target we have tested. And we quite in that case, we in the classical side it kind of went out, took a long time, even stuck a bit. But with D-Wave we were able to solve it. I don't exactly remember the time, but it was around 4 minutes or something for 6,000 targets.
Okay, and the answer to the question about use of the hybrid solvers versus the QPU?
So hybrid solver we were using CQM only,
So
and
CQM.
yeah, but we in the later stages we wanted to go with BQM and maybe have our own cubometrics, because that gives more tuning power to us. So, but as we have been a startup, we don't have a lot of time to go into that kind of experiment. But probably in future we will be coming up with a like more lower level of hybrid solver.
Okay. Is there some way to set up the algorithm so it simply won't return solutions if they don't satisfy the constraints? That way you wouldn't have to check if the solutions are valid.
So with quantum, we are already satisfying all the constraints, so you don't have to check that. But we were checking in case of Garobi and the simulated annealing. So this dark work is done for this benchmark only. But in real world, we have tested that it is satisfying all the time. So we don't have to put any kind of check for that. I hope that answers the question.
Okay. How does the problem scale with many targets, for example, greater than 1,000?
So we have for this question, you can see our benchmark paper which we have released. So there we have the graph where we have seen that in the classical it quite increases exponentially, but on quantum it's more like a linear. So you can have a better detailed answer in our benchmark paper.
Okay, I think we have time for a couple more. Have you compared your algorithm with other state-of-the-art quantum algorithms? This is not the first contribution in the field of satellite optimization. See Stolen Work et al. 2020.
So yeah, we can do this with QA as well. And in terms of classical, we have heard about Russian doll search, which is kind of heuristic. But if I mathematically see, I don't prefer like testing with heuristic, because as the number goes, it kinds of take a lot of time. So that I can say for now.
Okay, so we have now, Dana has now posted in the chat to everyone a link to the paper. Let's see, well, there are a lot of other questions. Let's see how many, a few others we can get here. One about the energy consumption of the quantum computer.
So I think this question I'll pass to the D-Wave team.
Yeah,
So, yeah, I have not much knowledge on that.
yes, we've done
Yeah.
actually a lot of work. The energy consumption of the quantum computer is actually very, very low. The only thing that the energy is really being used for is to power the classical
Yeah.
system that kind of sits there to handle the networking coming in. And then, of course, with CQM, you've got use of some classical resources. We do have some papers on our website kind of doing some comparisons, but kind of comparing a quantum computer to any kind of classical supercomputers, it's like night and day. So take a look at the D-Wave website under publications and you'll find some answers to that. Okay, I think with that, actually one last question here. Will the solution still work if we want to introduce new constraints?
So we are handling constraints, whatever we could do, but for the new constraint, you have to actually reconfigure the Cubo, right? That is not done on the fly, right? That has to be done previously. So I think we cannot do that.
That can be done, right? So initially we did not take care of the weather, right? And this is what we also published in the paper, right? So without weather and with weather, what was the difference in the performance of the algorithm, right? So you can also add more constraint, and in the paper you can see what is the effect of adding more constraint, right? So we can do that.
Okay, so for the remaining questions that we have, I will send them along to the artificial brain folks, and perhaps they will be able to answer them over email. So thank you all very much, our artificial brain team, for this very interesting talk today. And thanks everyone for attending. Our next webinar will be more of an overview and kind of introduction to quantum computing. So for many of you, it may be kind of too much a 101 sort of thing, but we will let you know. We'll send out an email early next week with a link to the recording and to the slides. And again, take a look at the paper, and thanks everyone so much for attending. Have a great day.
Thank you. Thanks, Susan.
Thank you.
Bye.
Thanks. Bye.